So yeah, there's the agenda link here. It's been shared in the calendar or hopefully wherever you found this link, on YouTube as well. There are a bunch of resources. Yeah, this should be here. I've added a couple diagrams and we'll go over some of these diagrams afterwards. There's also the Json Rpc Spec from Ethereum, which may be an interesting one to follow along on, and we'll talk about some of the useful commands or RPC endpoints. But just at a high level, I wanted to cover a bunch of things in terms of just what Ethereum is and how information is structured on Ethereum and how we can get information off of it, as well as what are the primary trade-offs when we're getting information off of it and why these trade-offs have left us battling a uphill battle in terms of organizations being slow to load. Afterwards, we have a bunch of information on chain. I'd just like to go over kind of what the map looks like on contracts and how an Aragon organization is actually represented as a set of contracts, as well as a whole infrastructure of other deployed contracts that are there helping serve an organization. And then afterwards, we go into the off-chain parts where we're getting information. And this is mostly going to be talking about Aragon.js and how we're primarily fetching state and then pushing that state into the various front ends, whether that's the client, individual applications, or otherwise. And I hope we'll have enough time to go over everything here. One of the main parts I hope we'll get into at the very end here, because it requires a lot of this prior context, is just how transaction pathing works in the context of an Aragon organization. There's a lot of pieces, let's say, that we have to build up towards before this makes sense. And so hopefully we'll get there and then everything will hopefully get more clear. I'd like to primarily save Q&A for people other than Pierre and Gabby afterwards. So if you can, just like send a comment or message me somehow and I'll try to take a look at the end if we have enough time. This is meant to be about an hour and a half, and we'll see how we do on time. I haven't quite done this before, so we'll just go as we go and see if we need to go faster or slower in some parts. Now in terms of audience, primarily this workshop is meant to get a quick start ahead, or like get us on the same page about how we're currently getting information and how we can build new tooling on top of this to make it really easy for people to build and integrate applications on top of an Aragon organization. The way we currently do it right now, if you've seen the client, this front end here is really meant to be building into an organization. And now we'd like to expose a bunch of tooling that will make it really easy for you to build on top of an organization. And essentially this is one of the kickoff sessions to get everyone on the same page, so we all kind of understand what's going on under the hood. And and we get a good representation, and then we have a couple ideas of how to improve what we currently have and have different trade-offs. So before I go any further, just wanted to check in, Gabby and Pierre. Is there anything that we should add? Would you like specifically to focus on one part, or should I just start and we can go from there?
I would say try to reach to the transaction path with enough time. Could be interesting.
Okay. All right. I'll try to do that. At the latter part here, I'm also less prepared for, let's say. And it'll just be a lot of reading code and hopefully debugging code on the front end to see what happens. All right. Pierre?
Yeah, no, all good for me.
All right. Okay. So yeah, we'll dive into Ethereum 101 and just talk really quick about some base technology, how stuff works in the back end. So the primary thing I'd like to look at, if we go to the resources page, there's two parts. So there's the Json Rpc, which is really good for understanding the APIs that we have from an Ethereum node and the things that we can get from talking to an Ethereum node that are really easy for us to do. And then the other one is this giant diagram. This diagram is very complicated, but we'll break it down into some parts that will hopefully make, if you're not too familiar with how contracts, transactions, and events happen, that will hopefully break this down a little bit more and get us a better sense of how everything plays together on chain. So the Json Rpc spec, first of all, is Ethereum, essentially the web API against an Ethereum node that we can talk against. So you'll see a bunch of API requests, and there's like, I don't know, 40 or 50 of these probably. You can see the list is quite long. For the most part, day to day, we typically only use about 5 of these. So that would be, and quite a lot of these are actually obsolete now in some sense. But the main ones that we get into are ETH sign. This is for signing messages. ETH send transaction. This is for sending a transaction and requesting the signer, if you're attached to a signer, to allow someone to sign. Send raw transaction sends an already signed raw transaction. ETH call is to get information from the state of Ethereum, from the current block state. And then there's get logs. Where is it? There's this one here, that's right, get logs. And this one is to fetch events or logs from previous blocks. Now, to make a bit more sense of what is going on here, we do have to look at this big diagram a bit. And please, Pierre and Gabby, stop if you would like. Just interrupt me and we can get into some parts of this. So in terms of how the blockchain is structured, you'll see there's like a bunch of blocks here, and then you'll see there's a bunch of things coming off of each of these blocks. And again, this diagram isn't extremely complicated, but it's worth looking on your own time just to kind of get a sense of where everything is laid out. The most important parts that we'd like to focus on really are the ones that are related to the RPC requests that I just talked about. And those are transactions. You'll see these green bit here, the logs, which are this gray bit here, and then the block, which is this, I don't know what color this is actually. I guess it's yellow or some form of yellowish green. So these are the main ones. And logs, again, are essentially events. And we can break this down into kind of a more simplified diagram that I've tried to make. So we have just kind of some blocks that we have here. A block is this rhombus, I guess, the diamond. State is actually the diamond. Transaction is an oval, and event is a triangle. So if we break that big diagram down, we essentially have a chain of blocks which have transactions going into them and state attached to each of the blocks. So with each block, basically, there's a bunch of different data that's getting attached to that block. And we'll see here that the state and the transaction, they essentially match directly to transaction try, which is here. That's directly related to the transactions root. And then the state root, which is this orange piece, which is kind of represented here. Now, the actual data structures that are used are somewhat complex. And we don't necessarily have to get into them, but you can just imagine the try as a giant object, a key value store object, and the transaction try, well, maybe not the try itself, but essentially the transactions root being like an array of transactions that are getting applied in this block. So coming back to this, you can kind of see this as, again, the key value store. Here we just have balance. Let's say we have the state of something, the balance is 1. That slice of state is attached to the global state, which is attached to the block. And then at the bottom here, we have a bunch of transactions, each of which are applying an action against Ethereum. And then there's events that are emitted from these transactions. And then we'll continue on with blocks n+1, where each block is basically the same structure, but building on top of the previous state. Actually, there should be something like that, essentially, where each state is kind of derived off of the previous block state, and the state transition is forced by a transaction. So a user sends a transaction, it does something, there's a bit of logic, the state changes, and then it gets propagated. So you can see here we're basically incrementing the balance. There's a bunch of transactions, but let's just say there's like one transaction per block, and this first transaction gets us to 1, the second transaction gets us to 2, third to 3, fourth to 4th, and along with each increment, we get an event that gets emitted. So before I go any further, I just wanted to ask if there were any questions about this simplified model, and if we needed to go to the diagram to discuss any part there, or should we just continue on to talking more about the block transition?
I wonder about the link between the states, how they are linked also in some way with a hash as the blocks.
Sorry, say that again, Gabby?
I wonder how the states, because you draw this new line, dotted line, and what they represent the blockchain.
Right.
That,
so this
relation.
Yeah, the relation I'm trying to draw here is that the state is derived. The next state is derived from the previous state. So what I'm suggesting here is like let's remove these. If this transaction, if it does, and how do I do this now? Okay, let's say I do this. If this does an n+1 operation, here, the n of course comes from the previous state. So every time you apply this logic, it's basically a giant state machine where you like take the previous state, you apply some logic on top of it, and then you get the new state. So they're like
so in a sense you have like a proof to, or you can solve like a problem that makes sure that each state is correlated. Okay.
You can in fact actually do this, I believe, because what happens with the state is that it's a giant Merkle tree. It gets split up a whole bunch of times, and you can prove like if you have a slice of a state that you actually got the correct state at that point by the Merkle proof. And there is in fact a get storage proof. Actually, yeah, get proof. I believe it's this one, 1186, I believe. Yeah, I mean, you can kind of take a look here, but if I understand correctly, you're asking if like we can just take one element from the state and prove that we have it is in fact part of the global state.
Okay. Yeah, I was. It was more of a general question of the link between the two states, but yeah, this is more like what would be useful to use this get proof. So interesting.
Yeah, I don't think they actually have a good diagram here, but there's another diagram somewhere on the internet that basically shows how the state trie updates, because of course, if we look at this, right, the state is going to be really large. On Ethereum right now, it's some tens of gigabytes, I believe. And so, of course, every time you make a block, you don't want to recreate all of the state. What you want to do is only include the diffs in that state, right? So the data structure that they've used effectively allows for this, where they may change, like here, if we have the left and the right, maybe you've updated this value or this leaf, and this part might change, but the other ones will refer to the previous values as before. So the diff is like can be quite small between different storage movements.
Perfect.
Okay. Just revert a bit. Okay. Yeah, should we move on? Pierre, anything to ask?
No, we're good.
Okay. All right, so we can get into kind of the block transition that happens when I apply a transaction or a set of transactions in a new block. Effectively, so a transaction holds a bunch of data. It holds a from address, a to address, the value of ETH getting sent, and some data to use from the contract, and then a whole bunch of others that don't really matter in this simplified representation. And the thing I wanted to represent here was just how we talk to contracts. So the transaction will be included in block 2, and the to address will be talking to this contract. So effectively, we're telling Ethereum, hey, I'd like this contract to do something. Here's the data. Let the thing run. It has logic built in, and I'm going to start updating. Like the contract will do whatever it needs to, but it may update state. So this is kind of where some of these concepts happen with the storage root and the virtual storage. The contract itself is kind of tethered to the chain by storage. So in some part of here, you'll see that there's a bunch of like more data inside this, which is effectively where the contract code lives. And the transaction we're sending is basically triggering that contract to do something. In this case, it's n+1 again. So what we're saying is, do something here, and then for this contract's own slice of storage that it owns in the chain, go do something with it, and then it'll set the new state. And it's kind of a closer look at kind of the things I was describing just previously to Gabby above. In terms of how this is kind of linked, again, transactions, both the transactions and the receipts are tethered to each block, and the contracts are tethered to the state as well as the contract's own storage. In terms of the events that are emitted in the transition, what happens is, as part of the transition, the transaction will talk to the contract, and this contract will emit an event or a log that's kind of represented inside the transaction itself. So when we look at this diagram, we see that, okay, we have a transaction, it's going to go do something. It's connected to the block here, but there's a bit more information that gets added as a result of the transaction. So this transaction is the input, and then the receipt is, you can kind of review it, or you can kind of view it and understand it as an acknowledgement that this transaction happened, as well as extra data that happened because of this transaction. In some ways the receipt terminology might make sense, because it's as if, imagine you're like going to a cash register and you have a transaction. You provide a transaction by giving money, and then the person gives you a receipt back about what you paid for. And effectively, that's kind of what this data structure is doing. And the most important part here is the log entry. So you'll see that each log entry holds a bit of data, the address, the topics, the data, all of which are kind of encoded inside events in Solidity, or that's at least how they map to logs. And then each of these get bound to the transaction receipt, and this transaction receipt then gets lifted into a whole bunch of other transaction receipts and gets tethered to the block via the receipts route. Now, alongside the literal data that we get from the log, there's also a Bloom filter that gets applied with the log. And this Bloom filter basically is a data structure that makes it really easy to search for, or at least not necessarily really easy, but more easily to search for how logs, or whether or not a log exists. So if we look at the set of, if we look at the set of, the simplified representation, the set of blocks, what the Bloom filter lets us do really easily is just say, if I want event A, but not event B, does block 1, 2, 3, or 4 contain those events? And instead of having to go through each transaction and each transaction receipt to look through all of the events to do a match, The Bloom filter basically says, okay, I have the block. Let me just apply a simple information function. It's effectively an O1 operation, and so that's really quick. Does it look like this block will contain the relevant events for me? And with a Bloom filter, it's really easy to detect. It's kind of like, it may tell you that there exists something of relevance, but it's not always perfect. So you get false positives. And so you can start effectively like coloring these blocks. You can start going in and being like, okay, if I'm only interested in a certain type of events, this block looks like it doesn't have it, so we can gray it out. This block looks like it doesn't have it, so we can gray it out. But these two blocks look like they might have it, and so we're gonna mark them as ones that we're interested in. And then because of that, we're only interested in these events. If I can color these. We've effectively narrowed the search scope to a much narrower set of events and transactions that we have to look through to see if they're interesting. And this is kind of contrived right now where we have half and half, but you can imagine inside the current Ethereum blockchain, which has more than, I think, 10 million blocks now, maybe it's still 9 million, but that very quickly eliminates the number of blocks that we have to look inside and reduces the expensiveness of this operation. Okay, so I think I just said a bunch of things, and I'm wondering if this makes sense for you guys.
Yeah, if I remember correctly, one of the first time I used the graph, I remember that I believe when you do the schema, they are kind of using the Bloom filter in the back to fetch the events. Could be that the way, the case?
Yeah, it may be. It might be another optimization that they apply on their side, depending on how the graph is hooked up. Because as I understand it, the graph effectively, like as each block gets created, you have like 10 to 15 seconds to go over all of the events anyway. So it's not like that big of a deal to look through each, but they might have applied another optimization on top where they use the Bloom filter to not even do like a little bit of work if they don't see a relevant event.
Okay. I have one question that when you mentioned about the block transaction state, why do you say that the contract on state is virtual?
Yeah, the virtual storage.
Yeah, what is?
Yeah, so the virtual storage, it's kind of a concept I've made up in trying to explain this, because each contract, you can think of its storage as encapsulated to that contract. Like the contract can't talk to another contract, right? So if we had two contracts, contract A wouldn't be able to talk to contract B's state unless there were APIs exposed by contract 2 or contract B to get that state. That's what I mean by virtual. It's just like this slice of state here is really just inside this contract, and it can't be exposed to other contracts. Does that kind of make sense, or have I just confused you further?
Yeah, and now a further question: how that work in the proxies contracts that Aragon apps use?
Right. Okay. Yeah, we can definitely get into that. I haven't quite actually prepared for that, but yes. So let's talk about that now, since this question has come up. So let me draw a couple arrows here. Okay, now we have kind of the same representation, right? So let's just make this the proxy. Okay, so we have the proxy contract here, and then we have the base contract. Can we name this to the base contract? Okay, well, whatever. So the base contract has its own slice of storage as well. And in fact, what we would want to do is duplicate this as well and move this to be here. Right. So yeah, so effectively both the base contract and the proxy contract have their own slices of state that are both encapsulated to themselves. Now what happens with the proxy contract is when we apply the logic, there's the special opcode in Ethereum called delegate call. And we can do that here. I forget it, it's probably like that. And when we do this, what we're actually telling Ethereum to do is, okay, go talk to the base contract, apply the logic, apply the code that you have inside this base contract, but instead of using his slice of state, use my slice of state. So if I did an n+1 operation into the proxy contract, let me just draw that quickly. If I did this, and I think it's like that, yeah. So if I did this and went into calling this contract, the first step that it would do, the proxy contract, it'd be like, oh, you're trying to call increment. I'm going to defer that logic to the base contract. And the base contract, it's going to basically load its code, and effectively then it becomes the same code. But instead of using the base contract's balance, it's going to use the proxy contract's balance. And so increment will look at it and see 2, and then he'll realize, oh, like the code I'm trying to use is just n+1, so I'm going to make that 3. And then the base contract comes back, and his storage hasn't changed at all.
Great. And maybe we can discuss it later, but one thing that I was not fully understanding of sometimes of the base contract is why do we need to reserve part of the memory to not replace it in some cases, because the assignment of new places in the storage was made independently of, or I mean, randomly, or.
So in terms of keeping memory, do you mean the previous version where we had the storage essentially blocked off?
I mean, for example, you need to know what is the app ID of the app that you are interacting with.
Mm-hmm.
So do you need to have that information in the base contract storage?
So all of that information lives in the proxy contract. Because before we can do the delegate call, we first have to know where to delegate call into. And effectively all of the proxy, all of its own logic inside itself is about determining who to delegate call into.
Okay.
Yeah, if we want to just quickly look into the contracts here, where is it? Yeah, on proxy base. So we can see here, no, not this one. Is it this one? Delegate call, constructor. Yeah, it's app. Where is the fallback? trying to figure out where we're doing. Okay, yeah, so it's a bit of a, there's a bit of inheritance in terms of this, where there's 3 or 4 contracts all built on top of each other. But the lowest, or yeah, let's say the lowest starting place is the delegate proxy that we have in Aragon OS. And all it does is expose a single function, which is doing this delegate call. And you'll see that we provide the address as well as the data that we want to call into. So as I was mentioning, the entire job of the proxy is basically to get both of these and put them into this function so that it can do the delegate call properly. One level above this is the possible delegate proxy, where delegate forward, right? So this is where we call delegate forward, and you'll see target comes from implementation, and the data just comes from the transactions data. This message.data is effectively this data here that gets sent with that transaction. And if we go a bit further up in terms of implementation, app proxy, I believe base, no. App proxy upgradable. You can see that we get the implementation address here at the highest level of the app proxy. And it effectively does a bunch of calls and a bit more logic to essentially just return an address that we can then put into the delegate call. And yeah, basically go through that.
Okay.
All right, so I think we went on a bit of a tangent, and we were previously at the events. So yeah, how this looks, I was just mentioning the logs bloom. The event is tethered to the block via the logs bloom, as well as the transaction receipt. And you can see here there's a bunch of data inside the event. And the way that we can kind of fetch event, let's call it, is either by getting the transaction itself and looking through the transaction receipts logs, like going in through here, go finding the transaction receipt, and then go starting from there to find the logs. Then we can see that in transaction. You can see here when we use get transaction receipt, there is an array of logs as well as a logs bloom. And both of these correspond to that information, an array of logs and a data structure for the bloom filter. Or the other way that we can do it is using a from address. So when we look at get logs, you can see here that one of the parameters is the address that emits the log, as well as a bunch of other things that tell us to filter where to look to make the operation faster. And so here, this from address is what's represented there. Each event encodes the address that emitted it, and that's how we can use that to effectively go through and just like find the most interesting ones. Because we have a bunch of other filters where all of these events may look the same, but maybe this one is from a different address than this one. And so we can also say, okay, there's another operation. This one doesn't look that interesting to us, or this one. And again, we just continue filtering through these events to make the data smaller and easier to consume for whoever needs to consume it. And also to generate, because getting this, as we'll get into, is one of the most expensive parts and why things are quite slow right now. Okay, yeah, the next part I was going to talk about was the Json Rpc, which is something that we've already been touching. But just as a visual representation, I wanted to show the types of information that we can get and where they correlate to the different parts of this diagram. We'll start with blue, which is the get transaction RPC requests. You'll see that there's a couple of get transaction RPC requests. if I go to the top, there is by hash, by block hash and index, and like a whole bunch of these. All they effectively do is they tell the node, okay, I want a transaction, go find it for me, give me the data that was related to this transaction. And we can see here that a lot of that is just like what block number it was mined in, the from, the to, the value, and the data somewhere, the input, the data. And all of those map, of course, to the things that were here. The next one, get transaction receipt is similar. It just kind of comes with a slightly different set of return values. Get transaction receipt, you'll see it adds a bit more. It adds the logs and the logs bloom. And it's just really just a slightly different form of the transaction. The next one is this green or the teal color, which is ETH call and get storage at. Both of these, the important thing about both of these is that they operate at the current head of state. So when we were talking about the chain of state here, we see that each block actually carries with it a state. Now this, of course, gets quite expensive to keep. In fact, that's why full nodes, or sorry, archive nodes, who do keep all of the previous versions of state are so difficult to sync. It's because they have like 10 terabytes worth of data at this point about every single block state. But for the typical node, when we use APIs against it, we can only fetch the current block state. So this set of APIs is really about getting either running a transaction against the current state. ETH call allows us to send a fake transaction, not actually sending a transaction that will cost money, but just to run an operation against the chain and tell us like what happens, what comes back. Or it can also allow us to get storage from the current head of storage. And again, it only applies to this area. So we wouldn't be able to use it for this block back here. And then finally, the red is ETH get logs, which is something that we were talking about. It's really about going through each block and trying to fetch as much relevant events as you'd like. And just by going through every block, you can imagine that this is the one that is very expensive to do on a normal basis. Okay. Yeah, about these, I think we've been touching them for a while, and we probably have some familiarity. But just in case, Pierre and Gabby, is there anything that we'd like to dive a little bit deeper into?
No, all good for me.
Okay.
I wonder, when you say that you can reply a transaction, what is happening in a bit, just in a small more detail.
In terms of faking a transaction, do you mean, or replaying?
Yeah, faking it.
Faking it? Yeah, so ETH call, let me just look at ETH call here. You'll see that ETH call effectively gives you the same parameters as what a transaction would include. So send transaction, you'll see send transaction, like these parameters from to gas, kind of gas, value, data, and nonce. They're very similar to ETH call, almost one for one the same. And it's like the description pretty much tells it already. They're just running a transaction as if it happened, as if it was mined, but not actually doing that. And the important thing about this and why this is cheap is because we don't propagate that transaction and we don't actually change state. So we're effectively just calling, like running a fake test, as you will, against our local node that we're connected to, rather than propagating it across the entire network, the global world network.
Okay.
Okay. Yeah, so the next thing that I wanted to touch on, stemming from the Json Rpc, is just a bit about non-determinism. So Ethereum, as I just mentioned, was a world state. You can imagine having everybody sync at a world level is very difficult. There's just physical difficulties, right? Light can only go at the speed of light. And that means when I try to go between like Tokyo and I guess it's New York, probably that's the longest, one of the longest, that's half a world way away. And that's at least some 100 milliseconds, or maybe I'm getting the math wrong, but that's at least like some difficulty in timing. And of course, all of the network and whatnot only adds to that. So it's impossible for us to get completely deterministic state from every ETH node that we talk about. And the case that I like to illustrate here is just something that happens once in a while, depending on which nodes and how the nodes you're talking to operate. So usually when we're connected to an ETH node, it's a very single connection. It's like you either have it set up locally, you have it on a server somewhere, or maybe it's on your cloud provider, and you're just having a single node that you're talking to. And effectively, that's been a lot of our own infrastructure, but we've since moved on. Now, that can only handle so many requests, right? If you think about it, each node needs to both sync as well as reply to all of these API requests. And given the state of the network, there's just a bunch of calls that are getting made. So it's getting very, very slow unless you start adding more and more nodes. But as you add more and more nodes, each node is effectively running the same transition algorithm every time. And because of that, you don't actually know if you're talking to one that you'll get the same results as if you talk to the other one or multiple other ones. And this is what I really mean by non-determinism, is that if you're talking to only one, you can be sure more or less that the state is going to be fairly similar and fairly consistent. But if you start making a request to one and then doing another request to a second node, the results are going to vary, or probably going to vary over the long run. And you're going to see some weird results. One main thing that we've seen in the past is just with Infura. Infura has a bunch of nodes, of course. They handle some ridiculous number, probably millions of requests every minute or every hour at this point. And so they have a very large set of nodes, but they make it seem as if you're only connected to one node, and they hide all of that complexity behind their APIs. But one thing that has made it quite difficult is just this concept of like what you can expect in terms of like a race condition. For example, here, if I do an ETH get logs and I get all of these events back, you can see that I get events from both block 1 and block 2. But then if I do another request with ETH call, that might go to a different node, and it might kind of get messed up in their backend. And doing this only gets me state from block 1. And this is bad, right? Because we're effectively saying, when we get this log, it's like, oh, great, we have all of this new information from block 2. Now let's dive into this event. Let's try to get something from the state. But this call is only getting applied against block 1. And so we have very inconsistent world states between the two of these. And this is a really difficult thing, but this is why a lot of times we have either retries or we have long delays between getting the event and actually using that event for something. It's because we're trying to like increase our probability that both of these will settle, and the second call here will be applied against the proper block that we wanted to apply against. Okay, so that was one source of non-determinism. The other source of non-determinism that I don't have a diagram for, but is in this diagram, is just, actually I'm not sure if this is really, actually this doesn't have this other set of non-determinism either, but I can quickly draw it. And if I just do this, let me try and copy, draw it somewhere. Okay. The other source of non-determinism is what we call block reorgs. And so imagine this is our world state right now. We have block 1 through 4, and all of these have gone in mind. But alongside block 1 through 4, there was a competitor. There were this whole other chain of blocks getting mined, and it's just kind of like doing its own thing. We're not quite sure what's going on, but some nodes are mining them. And at some point, let's call these actually 4, 5, and 6. Actually, this is 5. And at some point, this is going to turn potentially into what looks like actually, let's do this. This is all really probabilistic, but we may have some weird scenario where this happens, where after a couple blocks are getting mined concurrently, how do I ungroup? We get a total shift in how the blocks are organized. So previously we had kind of two competing sides, and then we were like, oh, actually all of these are valid. They don't collide, they don't do anything wrong. And some nodes have started picking up on this, and they've started reapplying these other blocks on top of it. And theoretically this can happen. I've never seen it, like, it's hard to catch unless you know kind of what you're looking for and you have scripts to catch this, but it does happen on a fairly regular interval on Ethereum. And so the problem with this is, let's say we tried to get the state of here and we acted on it, and then like 10 seconds later this happens, and now the state will look completely different, or could look completely different. And the only way to really protect yourself against this is to say that, you know, past block X, it's very unlikely that we're going to get a reorg, and so this seems like a safe block. And this will start making a little bit more sense about why I'm talking about this as we get into Aragon JS. But it's effectively a problem that we've had to deal with when we're listening on each block and saying, okay, there's information that we can use, and then the order gets switched. It's just very confusing, and we may actually have the wrong state applied depending on how these blocks go. And that, of course, is very bad, because then we're out of sync with the chain, and all sorts of crappy things can happen, and there's no way for us to know, like, outside of reapplying all the operations again. Okay. Yeah. Any questions in terms of the non-deterministic behaviors? I'm not sure if this has made quite a lot of sense, but hopefully the diagrams have helped. Yeah, in terms of what can happen.
Yeah, interesting.
Okay. So that was pretty much it for Ethereum 101. Before I move further in terms of the agenda and how Aragon organizations look on chain, are there any other parts that we'd like to dive into off of either what I had here, or if you're looking at this diagram, something that looks interesting and I didn't talk about, or you'd like more information about? Okay, sounds like we can continue. It does look like we're getting a bit over time. I've spent now, yes, that was about 45 minutes talking about Ethereum. So I'll try to keep this going. That does mean that for anyone who is watching, this will probably last a bit longer than the 1.5 hours when we actually get into the Aragon organizations. Okay, but let's dive into Aragon organizations and how they look on chain. So I've drawn a bunch of diagrams here, and they're kind of like a simplified version again of what the contracts look like on Ethereum. Each of these blue rectangles, or sorry, not blue, but gray rectangles, represent a deployed contract somewhere on Ethereum. And there's a link here to the deployments. We have this on GitHub. it will tell you pretty much everywhere these contracts are deployed, along with recommendations. So you can see that there's a bunch of these. If you pop them into Etherscan, you can see what contract they map to and when they were deployed. But they're represented all here in this diagram. So starting from the left, we have ENS, which is a totally different concern. And then we have Aragon ID, which is something we've built on top of ENS to register names on the aragonid.eth subdomain. And then we have here in the middle the Aragon OS base contracts, and there's a bunch of base contracts that are deployed. You can see the kernel, the ACL, as well as another app that we'll talk about later. And then there's a utility contract called the call script executor, which is related to the EVM script executor. The way these are all linked on chain is, everything is effectively built on top of the base contracts. And for gas purposes, both gas and as well as upgradability concerns, each Aragon organization is actually just a set of proxy contracts that map to the bases. And this is why Gabby was asking about the proxy contracts before. In terms of how all of these are hooked up, the bases are linked into a factory contract, the DAO factory. This one, again, you can find here on the DAO factory. You can see on Etherscan, this is the latest DAO factory contract. See, it's a DAO factory, and you can read the contract to find, I hope you can read. Yeah, you can read the contract to find the linked addresses. So the base ACL here, 953 or 9F3, correlates to this 1.1 version that we've deployed, and the base kernel 2B3 applies to the v1.1 that we've deployed. So both of those green links here, I've tried to keep the green links similar. Anything green is a state representation. Anything blue is a transaction, and then anything red, we'll see later, is an event. So if we dive in here, yeah, as we just saw, the DAO factory is linked to the kernel, the ACL base. And then there's this other thing, this other factory that is kind of connected, and the DAO factory also uses. But how we create organizations, the DAO factory has created, or the set of DAO factories, as you can see, there's 4 DAO factories that we've used now, depending on different iterations of our contracts. They have deployed every single Aragon organization that we know of today, or at least the official Aragon organizations. And each of them do this with a transaction. And when this happens, when this transaction happens, it deploys a whole bunch of other contracts. Well, proxies, let's call them. Here, in terms of just the DAO factory, we only get 3 contracts, but as we'll see afterwards, there's a bunch of other contracts that we can get into. But yeah, so when the DAO factory, when you call new DAO, this is the one that creates this bare organization, which only has the kernel and the ACL, and as well may include the EVM script executor if this was attached. So if I find this DAO factory, we'll see that there's a ton of internal transactions here. And this one specifically, this 1.11, is for the Dandelion organizations. So you'll see if I can see all of the transactions. Maybe it'll tell me all the transactions. 540. Okay, that's quite a lot. That's more than I expected. Maybe it's not quite that many. But anyway, so we can see here that each of these transactions is basically mapping to a transaction being, an Aragon organization being created. And the result of that transaction, that internal transaction, will be the creation of a set of contracts that are then used as the shell of an organization, and more will add on top of it. If we kind of jump from this to kind of the full template experience, we can see that the factory is just kind of sandwiched. Another factory, a template, an organization template, uses the factory to deploy even more contracts. And that's what's happening for most on-chain organizations now. They're deployed using a template, and from that template, we have an entire set of organizations, or an entire set of contracts that map to an organization. If I go to, for example, a Rpc organization, you can see this list of contracts that get deployed. And if we just dive in quickly, so this organization tab, this address here maps to the kernel. It maps to this guy here. And I actually forgot the ENS thing, but let me just add that there. And so if we have the Aragon ID ENS subdomain, it gets mapped to the kernel, and that's how we find this. Anytime you see this ENS, we resolve it to this address right now. And then we see we have a bunch of other contracts. Right now we have 4 that get displayed here, and each of those contracts get mapped to one of these gray boxes. And all of them, as we'll see, are coming from the organization template. So if I look at the deployments, if I look at each of these transactions or contracts on Etherscan, you can see that this transaction, 460, was the same for all of them. So that means each of these were created in that transaction. And this contract, if we look at it here, this is me who created it. I call this contract B99 is, oh shit, it's not on mainnet. If this was on mainnet, you would see that this is a company template, and it would map to this gray box here. Let me actually do this against mainnet so we can see the verified contracts. It's a bit nicer. All right, so this is A1. This is the organization that we use internally for payroll and all sorts of other things. And we'll see here, this is the kernel. We'll see that this is indeed the kernel proxy, and that maps 6351, 6351. And we'll see the transaction that it got created on was AB29, and all of these other applications, contracts, were AB29 as well. And if we look inside here, this person called this contract, which was a democracy kit or a template back in the day. And when that happened, a whole bunch of things happened. This was the new organization, and then it installed a bunch of apps, and each of these will map. If we look at the address here, this first element, each of these will map directly to the list of addresses that we see here. And then, yeah, there's a bit of extra information here in terms of how these apps are actually built. As we were talking about each of these apps, all of them are proxies. So the kernel, right, everything in this brown box is a proxy. And again, they represent the organization. So the kernel is linked back up to the kernel base. The ACL is linked to the ACL base. The apps, they're linked to their app contracts. And we can see that on chain. If we look at the kernel proxy, if we read the contract, we can see that the implementation is 4A6. And if we look into this contract, it is indeed the kernel. And 4A6, if I look here, this is the V0 version of our kernel. And I don't actually have the ACL contract at hand. But if I look at the ACL contract, it's an app proxy upgradable. So that's what I mean by the proxies. If I read the contract, its implementation is 8.1.f7, and if we look at 8.1.f7, it's going to be the version 1 of the ACL. And we'll see for all of these contracts, they're all proxies, proxy, and they all have an implementation address that if we go into it, will show that it's an app. This is the token manager that links to here, and this one is finance. So we kind of went through the chain, went down from this, which was a proxy, into the finance base contract. So hopefully I'm not going too fast here with the tabs, and the rendering okay. But yeah, that is kind of traversing the entire organization on chain. And yeah, we see a bit here with the blue. This is the Cradle organization transaction. It's effectively the same here, except it's coming from the template instead. And this transaction gives us a couple more events than just the one that the DAO factory would give us. Specifically, it tells us when the DAO has been, first of all, created, the shell, which is deploy DAO. I should actually reorder these. Just do that. So first, the deploy DAO event is emitted from the organization template. Again, we can see that here. If I go into this transaction, if I think I should be able to see the events. Where are the events? Maybe not. Oh no, this is the wrong one. So if I go here, yeah, there's a whole bunch of events. Deploy DAO, we'll see here, this deploy DAO, this event was what created the initial shell, effectively this part, and it just has the bare minimum for an Aragon organization. And then when we get into setup, where is setup? Deploy instance, confirm subdomain, address changed. Okay, one of these will be the DAO events, and when that happens close to the end, that's when this whole organization has been set up alongside all of the permission and everything else.